when we want to derive learning rules for neural networks from first principle, we typically do this by gradient descent on a loss function. So, and this often leads to implicit or explicit symmetry constraints, either on the connectivity or the weight updates. So one famous example here is backpropagation, where you need to transpose of the weights in each layer to transport meaningful gradients down to deeper layers. And this transpose is basically a copy operation, which is kind of physically implausible, which is also why backpropagation is termed to be biologically implausible. And this can also pose us challenges when it comes to neuromorphic hardware. Of course, you can calculate the gradient, you can outsource the calculation of the gradients to an external CPU, but it would be much more efficient to do it really in an online on-chip fashion directly on the substrate. So this is what is called the weight transport problem, and I want to solve it in spiking systems. So here is my idea. The thing is that each weight leaves a characteristic mark in the spike timing statistics of the neurons. I think this is clear. So let's have a look at this simple two-neuron system where we say the green synapse is a bit stronger, so that means that neuron J will on average answer to a spike from neuron I a bit faster than the other way around, right? So if these two weights would be equal, then you would observe a symmetric distribution of these delta t's, so the time difference between pre and post spikes. However, if the weights are unequal, then you see, as in this case, they are skewed. And since these two synapses observe the same spikes, they also share the same statistics, just flipped at the y-axis. And this then we can basically harness to construct a learning rule that symmetrizes the weights, simply by taking very standard STDP with this kind of anti-Hebbian STDP kernel. So if you have a surplus of small positive delta t's because your green weight is too strong, then you also have a surplus of negative weight updates, and green will become smaller and orange would become larger. And this principle I call SAL for spike-based alignment learning, and it's designed to be an add-on to sort of augment existing error collecting learning rules that suffer from the weight transport problem. Next, I would like to show you two use cases where I employed it to show that it actually does something useful. The first use case are generative spiking networks for Bayesian computing. And basically these are kind of spiking versions of Boltzmann machines, and from their Boltzmann machine archetypes, they inherit the need for both symmetric weights and symmetric weight updates, right? And this poses a challenge when you want to implement it on noisy neuromorphic substrates, and that's what I simulated here. So I simulated with a noise on the initial weight matrix, making the weight matrix prior to training non-symmetric, and also I simulated noise on the plasticity, which also lets the neurons or the synapses diverge further during training. So this is what you see here with the orange line, and this also like hinders training. And then when you employ SAL, then first of all you can realign the weights and then keep them stable in the align phase, and then you can achieve better performance. And my second use case is a use case from the example, the physically plausible backpropagation. So in this case, I employed the model of cortical microcircuits from Sacramento et al., and I turned it into a spiking version. And here I could show that, first of all, also SAL is able to align the backward weights with the forward weights, so in this backpropagation-like fashion, and it's also a key ingredient to improve upon feedback alignment and to be a key ingredient for the physically plausible and local error transport in such systems. So with this, I would like to thank you also for giving me the opportunity to present my work here. And if you want to know more about my project, I have a poster, and it's right there on the first floor on the southern side. Thanks.